are in Cowes Harbour. We've just picked up Andy, and we are going to talk about quantum computing. It's very, very rough, so I'm going to focus on driving while Andy, if you'd like to introduce yourself.
Sure, thanks Phil. Yep.
Good.
I'm Andy Stanford-Clark. I work for IBM UK. I'm one of IBM's distinguished engineers and a master inventor with more than 40 patents. For the purpose of this conversation, I lead the Quantum Ambassador team in IBM, which are a team of about 20 people who are trained and allowed to speak publicly about IBM's quantum computing story. So that's why I'm here.
So it's quite useful in the context of making a video about quantum computing.
Exactly,
somewhere. Yeah. So, and Andy's obviously, so I've known Andy for a number of years. He's part of the tech Solent community, and Andy has actually done a lot of really good work in explaining quantum over the years, last few years, to our members. And it's changed a lot. So I think it's useful just to get a little snapshot of what's going on today. I mean, Andy, do you want to just give us, for the purposes of now, just a little introduction to what quantum computing is?
Sure. So quantum computing, big scary topic. First of all, it's quite unlike anything that we have today. So we refer to today's computers as classical computers. So I'll be referring to those from time to time. First of all, quantum computers don't replace classical computers. So you're not going to throw away your classical computers in your data center and buy a big shiny quantum computer to replace it. It'll always be the case that classical computers and quantum computers are working side by side to solve some really big problems. Now, quantum computers are particularly good at some things and no good at all at other things, which is why we still need the classical computers. So trivial things like loops and if then else, quantum computers don't go anywhere near. It's a completely different way of thinking about computing. And from that point of view, to be involved at the beginning of a whole new computing paradigm is a once-in-a-lifetime opportunity, so really, really exciting. So quantum computers are particularly good at solving really big, exponentially growing problems. So they tend to be the kind of problems that we shy away from as classical software engineers. We refer to them as intractables, problems you just can't solve in a sensible amount of time using a classical computer. Quantum computers, because of the way they are built and operate, are particularly good at solving these exponentially large problems where you've got a 2 to the n search space if you've got n qubits, which are the building blocks from which quantum computers are made. So that allows us to solve problems where you, for example, have to search a really large space, or where you've got to represent a really big, hairy problem and then nudge it towards a solution. And it's very much an iterative process as you converge towards a solution, which will immediately tell you that programming quantum computers is totally different from programming classical computers, which is why people like me, who are classically trained as software engineers, have a real problem getting our heads around quantum computing.
Andy, can you give us an example of the sort of problem that quantum can be used to solve?
So, really good problem that we can solve with quantum computers. Well, there's three main categories, but the main one that's showing promise at the moment is computational chemistry. So this is where you're actually simulating nature by modeling a molecule inside the quantum computer and then finding out its lowest energy position and then merging it with another molecule, as we do when we're looking for new pharmaceutical drugs, for example. Today it's really, really simple. We can because of the small size of today's quantum computers, we can only simulate really simple molecules like beryllium hydride, which is a tiny, teensy little molecule. But quite soon we're going to be simulating much bigger molecules and using them for really interesting chemical exploration. Like, for example, in fact we're already doing this, new EV battery chemistry with Daimler-Benz, or looking at new stealth surfaces for fighter aircraft.
So, and I suppose, on the way over, I gave the Phil Clark version of quantum computing, which, as you can imagine, was fairly noddy. You sort of just explained that it's not really for everything. Is there anything that would be a bad example of where you use quantum? Where is it not worth going down the quantum route? That might be a stupid question, apologies.
No, it's not really, no. So quantum computers will be able to solve really big, hairy problems, which means you don't want to use them for solving smaller problems because the setup... Whoop.
Nearly lost the cameraman, I've got to keep that in.
Because the setup of the program and the time taken to run each iteration and then the convergence to an answer means you're probably much better off and much quicker solving it on a classical computer. So you always have to make a value judgment whether it's best just to run the flat out best classical algorithm or whether it's best to switch to the quantum processing. Now in the future, we probably won't need to worry about this because the libraries that we use way down in the depths of applications will just know that they've got a quantum processing unit, a QPU, on board in the same way as a GPU-enabled system now knows it's got a graphical processing unit and will automatically make use of that. So most of us won't have to worry about the functions and gates and circuits of a quantum program. We'll just use our applications and just use it to solve much bigger problems much quicker.
So I think maybe if we just call it a day while I get out of this very rough sea,
Yeah.
and then we'll go and talk about the history of quantum, if that's all right.
Sure. Okay, looking forward to it.